Today I would like to talk about how we can deal with RBD simulations in USD and Solaris in a really optimized way. Let's first go into our stage context. Okay, so let's first talk about how we would do this if we were working in a multi-artist studio environment. So the first thing that would happen is that you would get a shot USD layer from your layout department or animation department. And here you would have your shot assembled. You would also have a camera. Don't worry too much about what the shot looks like. This is just for illustration purposes. So as an FX artist, let's say it's your task to destroy this rubber toy here hovering above the ground. So how would we go about doing this in the most efficient manner? To start off, you would create a layer break because you don't want to be saving anything before this point. I'm going to create a null and let's call this FX start. If we take a look at our scene graph down here, we have some folders, camera, environment, and some props. And this rubber toy asset is what we're going to be simulating. So our goal essentially is to take this asset, we're going to fracture it, and we want to write out a USD file, just a non-time dependent static USD file of that high-res fractured geometry. We then take the points output by the RBD simulation and we want to move those high-res pieces using those points. And the only thing we want to write out that is time dependent is the transformation data of those points, and that's going to be really optimized and fast to work with. So we're going to be writing out just those two USD layers, and I'll show you a few ways how we can go about doing this in a optimized way. Now, one way you could go about doing this, and I actually think this is good in most cases, is to use the RBD Destruction node in Solaris, which is a pre-packaged node that does most of the work for you. You can see it gives us a bit of an error by default. So we want to choose the primitive we're going to simulate. And I set the time range to be just 24 frames for speed's sake. So let's choose our rubber toy primitive. And I'm also going to select our ground here for the collision primitive. The collision primitive does by default get imported each frame, so let's just set that to be the start frame. And if we hit play, we can see our rubber toy is being simulated all inside of LOPs. And this is good, but by default this is set to use the procedural method, and I actually haven't found a good way to save out the transform data using this mode. So while this is quite optimized and very quick, I found the best way is to use the transforms mode here. And you can see the moment I turn this on, we get a bunch of primitives, like new primitives inside of our rubber toy asset here, each corresponding to a fractured piece. And we also have a inside group as a subset for all of these. So if we dive inside this RBD Destruction node, we can see this is actually just a SOP network, and we can do all of our custom simulation settings and fracturing inside of here. And the node is going to take care of all the USD stuff. So to save this out to disk, we want to check this static save path here. And I'm just going to copy a path to a folder I created on disk. And I'll save that as a USDC file, because it is geometry data which can be heavy. So now we have that set, and if we go into our scene graph layers, we can see that we have a save path set to the layer here. Now we also want to save out just the transform data for this. So to do that, I'll use a configure layer node. Let's paste the same path in the save path, and I'll say this is the RBD points. This can also be a USDC layer, and I'll make sure to turn on all of these time settings here. I'll also set the up axis like that, and I'm actually going to start a new layer because I want to reference both of these two layers in just the final FX USD layer. So let's create a USD ROP, give it the same path, and this is going to be the FX master layer, and I'll use USDA for this. We also want to render out the frame range, so let's try to save this to disk and see what this gives us. So if we take a look at my files on disk here, we can see this just saved out 3 different layers, which makes sense. We have the FX master layer, and we have the points, and we have the static. And you can see how, this is a very light shot, but the file sizes are quite small. Now let's bring this FX USDA in as a sublayer into our shot and see what this gives us. So by sublayering in this under our shot USD, we can see that the geometry that was static is now moving and being destroyed, just like we want. So this is absolutely one way you could do this. And again, if we take a look at what this node actually gives us, we can see that we have all of these pieces, each corresponding to one of the fractured pieces. And we have the inside group here. And this is actually really handy because we usually want to give the inside faces a different material. So what we could do, for example, is create a collection. I'm going to call this collection inside, and let's just control click this arrow here. And I'll just click one of the inside GeomSubsets. And then we can actually use wildcards to just get the rest of those. Like that. And I'm going to create a quick material just to show how we can go about giving each of these different materials. Let's give this a really strong color and an assign material. And the way you access just those collections is to use the percentage sign and then the name of the collection. So inside in this case. And I'll control click and select my material here. Okay. And I'll create a dome light just to the side, just to see what this gives us. Let's do a test render. And we can see we now have that material only assigned to those inside faces. So yeah, just a quick detour to show you how we work with these inside GeomSubsets here. Now, one thing I just want to quickly mention is, even though you don't have a shot USD or you're not working in a multi-artist environment, you could easily replace this here with just a SOP import or a SOP create, anything you created in Houdini basically. So let's create a SOP create. I'll dive inside. Let's do a rubber toy. We'll put it above ground. And instead of using our shot USD layers, I'll just replace it with this SOP create. And in our RBD Destruction node, I'll delete the collision primitive and let's just replace this with our new rubber toy here. And we can see this is working. All of this is also going to work, and also the USD ROP. For all of you that are working by yourselves, I just wanted to mention that. Although this setup is working quite well and this node is actually really good, I think it could be a bit difficult to understand exactly what's going on behind the scenes. I mean, we have so many nodes inside here and it's a bit unstructured. So I'm going to show you a different method we can go about doing this, which is perhaps a bit more advanced, but it gives us much more flexibility and control in terms of how we choose to save out our USD layers. Before we go over the next method, I just want to briefly talk about some basic USD theory, in specific how we go about using the path attribute and the name attribute to create our USD hierarchy from SOPs. So if you already know this, you can skip to the next section. Just want to briefly mention this. So I'm going to take our SOP crate. I'll just copy this over here. And if we take a look at this node, we can see that we have some settings. This is going to take the name or the path attribute and convert that into a USD hierarchy. So if we dive inside this node, I can create a primitive wrangle. And let's, for example, say that the path is going to be equal to rubber toy, geo, and shape. And if we go back into LOPs, we're going to see that the SOP crate actually respects that path we just created inside of SOPs. And the same goes for the name attribute. So I'll change this to name, and we can see we have the exact same result because of this path attribute here. So if we, for example, remove the name here, our hierarchy breaks because we are telling the SOP crate to ignore the name. And this is really important to understand because we want to take our USD asset and we want to fracture it, but we want the fractured pieces to have the exact same USD hierarchy as the non-fractured asset. So we basically want to replace the non-fractured asset with the fractured one. So let's take a look at how we go about doing that. Okay, for the next example, let's just reuse this setup we were using before. We can also delete our sublayer. First thing I would like to do is to create a SOP network. Let's copy the fx start null and I'll dive inside of the subnet. Now, obviously, to bring in our geometry from LOPs, we have to do a LOP import, and I'll paste the path to the null. This is time dependent by default because the time sample is set to animated, so I'll just turn that to static. And for the primitives, let's use the rubber toy topmost primitive here. Now we have this purpose menu here. If you know that you have an asset that has a render purpose and a proxy purpose, I would set this to render like this. In our case, I know we don't have a render or a proxy purpose. We have a default purpose on the geo, but that's not going to matter. So in our case, I'll just set the purpose to be star, aka bring in everything. Now we also have this traversal menu here. You want to set this to gprims. Gprims stands for geometry primitives, and it's going to filter out only the primitives in USD that contain geometry data, which is exactly what we want. If we take a look at our geometry here, we can see we have a packed USD. We actually want to unpack this before we do any further operations. So let's do a unpack USD to polygons. USD SOP create and SOP import nodes respect the path and the name attribute, and we want to take our already existing asset, fracture it, and we want those fractured pieces to have the exact same name or path as the original asset. We can see here, if we take a look into our primitive attributes, we have a path which is corresponding to the hierarchy of our USD shot. And we also have a name. Since we know we're going to be dealing with the name attributes in our RBD simulation, which is what the RBD simulation wants, we actually are not going to use the path attribute at all. So in this Unpack USD node, I'll set the path attribute to be name, and I'll turn off the name attribute. And what this is going to do is copy our path attribute into our name, which is exactly what's happened. Now, there is one really important attribute we have not talked about, and that is this USD XForm attribute right here. We can see that this is being copied by default to our points, but just in case, I'll make sure to be explicit about that, because we're going to use this USD XForm attribute to make sure our RBD sim transformations are correctly applied to our fractured geometry. We can also see we have a bunch of other attributes here. USD path, USD material path. I'm just going to delete these. So let's just delete anything that contains the name USD. So to summarize, after bringing in your asset from LOPs, make sure you have the USD XForm attribute and the name set as the original path attribute. One other thing I want to do to prepare our geometry for RBDs is to create a primitive wrangle, and I'm going to modify the name of this asset a little bit. Let's say that the name is going to be the current name plus piece. And I'm just using this to initialize the name of our fractured pieces before we actually fracture them. Let's do a RBD material fracture. And I can visualize this fracture with a exploded view. And the name of the pieces is getting appended to that piece name that we created inside of this primitive wrangle. And that's exactly what I want, because we want our actual fractured pieces to be a sub-component of the original shape primitive. One really important thing is that you can't have the piece prefix be this dash here, which it's set to by default. You need to make it a underscore because the original dash is not compatible with the point transform node. So just make sure you have that. And I'll actually do an additional fracture, and I'll turn off my second fracture here just to make sure that there's no limitations when it comes to this workflow. I mean, it's just regular RBD workflow. We just need to make sure we keep a few things in mind because we're dealing with USD in particular. So let's create a scatter, and I'll do a Voronoi fracture. If we look at our names again, it's probably broken. This has overwritten our existing names. So instead of overwrite in the name attribute drop down here, let's use append, and I'll delete the piece here. Let's see what our names look like, and I'll again put a underscore here. So now we have our initial fracture and the sub fracture, which comes from the Voronoi, and our naming is nice and clean. And this is actually everything we need for our fracture geo, and this is going to be our render mesh. So let's create a null and call this high-res geo. Now, one thing we should probably make sure we have at this stage is a rest attribute, and I'm going to call this pref because that's the naming Arnold uses. And yeah. Now the rest is basically just doing a regular RBD simulation. So just like you would normally do, I'll use a RBD configure. Again, I'm just doing a really simple example for this. Like I mentioned, this is going to be the fractured geometry that we actually end up rendering. So I'm going to copy this. Let's do a object merge. And I'll give this a null. And another thing we need is going to be the simulation points of this fourth. So I'll call this out RBD points. And when we work in SOPs, the regular workflow is going to be to use a transform pieces. So you would cache out this high-res fracture, and you would cache out your RBD points, and you would move those high-res pieces using a transform pieces. Most likely you would actually have a proxy geometry that you are simulating, so I'll just use a convex decomposition here to create those proxy pieces. It's going to be a bit faster to simulate, and you would simulate that and you would transform those high-res pieces using these points. And that's the workflow we're actually trying to replicate just inside of Solaris. So let's go ahead and do that. Well, like I was hinting towards previously, is you want to take this fractured geometry and replace the asset that exists in your scene with that. So let's use a SOP import. Just going to go over a few settings for this. This is going to be static, so we want to make sure we are not authoring any time samples with this. We can also see we have a bit of a warning that there is no save path set. So to fix this, I'll use the option here in the dropdown, merge sublayer into existing layer. I'll turn off the adjust transforms for input hierarchy. And what's really important here is that we only want to be defining the leaf primitives. And this setting is going to make sure we only define the primitives at the bottom of the hierarchy, which are the fractured pieces. Like we did before, let's bring in our inside group using this subset groups menu here. It's going to be inside. We can see we have generated a inside GeomSubset for most of these pieces. We can see some of the pieces don't have them, and that's probably just going to be some parts of the geometry that are individual pieces but were not fractured. Now we're running into a bit of a problem. We can see we have the original asset and we also have the fractured asset hovering above it. So what's causing this? Well, let's first go ahead and fix the original asset remaining inside of the scene. And to do this, I'm actually going to edit the properties of the mesh itself. So let's come into the shape here. And all of these orange values are going to be fallback values, aka these are properties that have not been explicitly set inside of USD, and we can double check this by clicking this legend, and we can confirm that the orange means fallback value. You can see that the blue is a default value, aka an opinion that has been set inside of this asset. So let's select only the default values like this. Maybe this one as well, and I'm going to right click and do an edit property. We can also do a shift enter, and for all of these I'm just going to say block. And by doing this we can see we have no geometry anymore and the asset that existed has been removed. Now we can go ahead and bring in our fractured geometry, and we have now fixed that initial problem. Another problem that we have is that if we compare the transform of this fracture geo to the original asset, we can see that this is completely wrong. And the reason for this is actually because the USD transforms are being applied twice. To fix this, let's go into the subnet again. And I was hinting towards this attribute earlier, but we're actually going to use this USD xform attribute now. So I'll use a transform by attribute. And I'll set the transform attribute to be USD xform. And by default, this is actually giving us the exact same result we were having before in Solaris. So we want to press this invert transformation. That's just going to reset the initial transform that the USD had. And that's what we need to do to apply the transformations of these RBD points correctly. So let's go ahead and do that. Below the SOP import, I'll create a transform by SOP Points node. This also gives us an error by default, no display node found. And this actually takes an internal SOP as a source. So let's get our RBD points. I'll copy the null and I'll dive inside the point transform node, do an object merge. And let's see what this gives us. Another error, path attribute not found. This node actually wants a path attribute instead of the name attribute that we currently have on our points. So the only thing we need to do to fix this is to rename the name attribute to path. And we can see we have now applied our simulation to a rubber toy and everything is working perfectly. So just to summarize how we use this node is you take the points output by your RBD simulation, you object merge them into the points xform node, you make sure you have a path attribute on your points that corresponds to the name attributes of your fractured high-res pieces. So I hope that makes sense. Now we can move on to saving our USD layers. So again, to reiterate, we want to save the static high-res fractured geometry as one layer, and we want to have the transform data of these points as a separate layer. So let's create a configure layer. And this time I'm going to use relative paths, and I'll show you how we can do this. So this is going to be the RBD static at USD. We can set these attributes if we want, and I'll start a new layer. We can see the second I press the start new layer, the node color of this changes, indicating that this is a separate layer. And let's do the same thing here. It's going to be the RBD xform. And I'm going to turn on the time settings. And finally, we can create a USD ROP, pass to my desktop. It's going to be our master effects layer, and I'm going to set the render frame range from stage. And what this means is that we have a start time and an end time set in our configure layer here. So this USD ROP is actually going to look at those values and only write those frames to disk. So if I, for example, set this to 24 and I write this is only going to write those 24 frames. One more thing though, let's come to our output processing. And like I mentioned, we were using these relative paths, so we have to turn that on specifically here. So let's turn on save path relative to output path, and I'm going to send this to the top using this arrow. And now we can save this. Now let's try to sublayer this FX layer we just created into our shot, and let's see what happens. And everything is working as we expect. Let's also talk a bit about motion blur and transferring velocities onto these pieces. We can actually do this with the point attributes to copy here. So let's dive inside, and I'll do a trail node just to recalculate the velocities. Set this to compute velocity, and I'll also compute acceleration. And we actually have to change these attribute names into their respective USD names. We can see we have a V attribute, a W attribute for angular velocity, and we also have this accel attribute for acceleration. We can go into the same attribute rename here. V is going to be velocities, W is going to be angular velocities, and accel is going to be accelerations. Now we just have to make sure we're actually transferring these attributes onto our pieces. So I'll just copy these names. Let's save again. And this should, in theory, help our motion blur when we do our rendering. So let's try to do a test render. Maybe I'll create a dome light. Although it's maybe not that visible, we actually do have motion blur. And turning on this option in the Karma render settings will accentuate that even more. Now, in some cases, what you might actually have is an asset that contains a GeomSubset below the mesh primitive. And I'll just create one just to show you what we would have to do if that's the case. Let's take our rubber toy, and I'll just add a prim. And I'll create a new prim called subset, and that's going to be of the type GeomSubset. And what you would have to do if your asset looks something like this, you actually have to deactivate that subset using a prune node. So how we do this is we create a prune node below our edit shape. The primitive pattern is going to be %type, GeomSubset. Make sure you capitalize it like this. And instead of using make invisible, you just have to set this to deactivate. And that's all you would have to do. So yeah, that's it for this video. Thank you so much for watching.